Okay, this tutorial is on the proof of that root 2 is an irrational number. And before we get into that, let's just clarify that an irrational number is a number that can be represented as a fraction, in other words, as the ratio between two integers. The approach we're going to use to prove that root 2 is indeed an irrational number is a technique called proof by contradiction. So what we're going to do is assume for a moment that root 2 is actually a rational number, and then see if we can find a contradiction, because if we can find a contradiction in that assumption, then that would make that assumption invalid, meaning that root 2 would actually be an irrational number. So if that's not clear, let me go ahead and just start writing it out so you can see what I mean. So assume that root 2 is a rational number. Now, if that were true, then what would be the case? If root 2 was a rational number, then root 2 could be represented this way. It could be expressed like this. It could be expressed as root 2 equals p divided by q, where p and q are positive integers. In other words, we could write p comma q are elements of z positive, which is the positive integers. Now, the reason that it's positive, that they're positive, they would be positive, is because root 2, we know that's a positive number. So it wouldn't make sense if either of these were negative, because we couldn't have a square root of a number being a negative number. That wouldn't make sense. Now, the next point we want to consider is also that this is the reduced form of root 2. So the assumption there then is also that p and q are co-prime. And what that basically means, if you haven't seen, I suggest you watch my tutorial on greatest common factor. I think I go into it there, but I'm just going to write as a note, that is the p and q have no common divisors other than 1. Okay, and you'll see why that's useful towards the end. But basically that implies that this is a fraction in its reduced form. So for example, it wouldn't be 4 over 8 because those would have a common factor of 2 and it could be reduced further. So what we're assuming here is that root 2 can be expressed as a fraction p over q, where p and q are both positive integers and they're co-prime, meaning they have no common divisors other than 1. Now, the first step in our proof then is going to, well, all we're going to do actually is just do a little bit of algebra first. So if root 2 equals p over q, then if I go ahead and square both sides here, so I'll just rewrite it first, then that would imply that 2 equals p squared over q squared. Because all I did was square both sides. So I'd squared root 2, get 2, square this side, and I get p squared over q squared. And then I'm just going to basically multiply the q squared onto this side. So if I rewrite that, I get 2q squared equals p squared. Now, this is where it gets kind of interesting. If 2 times q squared, we don't know what q squared is. It could be any number. It could be positive. I mean, it definitely is positive because that's what we assumed. But it could be even. It could be odd. It doesn't really matter. The point here, though, is if p squared is equal to 2 times q squared, then whatever q squared is, p squared is even, because it's 2 times whatever q squared is. So this right here would then imply that p squared is even. In other words, it's divisible by 2. Now, one more thing on this page, then I have to go to a new one. I'm running out of room. But if p squared is even, then p is even. Why? Because an even number squared equals an even number. an odd number squared equals an odd number. For example, 2 squared is 4. 4 squared is 16. An odd number like 3 squared is 9, or 7 squared is 49. And you can see that for the even number squared to be even, that would imply that p itself is even. Okay? So now we have the next step, which is p is even. And I'm going to put that on another layer. So since p is even, according to our logic so far, that would imply that we could represent it as p equals 2r. And r is just another integer. So whatever r is, doesn't matter. P would have to be 2 times some number, right? If it's even, which we've shown, according to our logic, is the case. Now going back to our original equation, we had 2q squared equals p squared. And now we're saying that p is equal to 2r. So what would p squared equal? P squared would equal 4r squared. So p squared here equals 4r squared. So now all I'm going to do is remove the p squared from the middle here and just bring both of these guys down. So I get 2q squared equals 4r squared. Now the next step is just, again, a little simple algebra. Divide both sides by 2. And then we get, and realize when I'm using this little weird arrow thing, that just means implies or it follows that. So if I divide both sides by 2 here, I get q squared equals 2r squared. And then that would imply that q squared is even, which we already shown before when we did p back here, that if p squared is even, then p is even. So if q squared is even, then obviously q is even. Now, what we originally, this is actually the end of the proof, because just from this fact here, we can say that this whole assumption we made is invalid. And let me show you why. Let's go back to the beginning. So now we've just shown that both q is even and p is even. Well, let me get a new layer going. P is even, which is what we've shown from our as an outflow of our assumption, and also as another outflow, q is even. Now, if they're both even, that means what? P is divisible by 2. And if q is even, q is divisible by 2. Now, that may not seem like it's a big deal, but if we look at the original assumption, that p over q is in its reduced form, and that p and q are coprime, meaning they have no common divisors other than 1, then you'll see doesn't make sense logically that could be true while also p and q are both divisible by 2, because that would mean they have a common divisor. So this whole section here implies, and I'll just go ahead and write it out, this implies that p and q have a common divisor of 2. And this statement there, here, really is the direct contradiction of our original assumption here. That root 2 is expressed as p over q, where p and q are coprime. So that in itself is a massive contradiction that only comes about if we assume that root 2 is a rational number. So since it can only either be rational or irrational, and if we assume it's rational and then it leads to an obvious contradiction, then the logic there is that root 2 must be indeed a rational number. And I'm just going to circle that, which I think makes sense actually. Now, I suggest, if it's not totally clear, to go back and watch this tutorial again. All the steps are there. Yeah, I hope you enjoyed this tutorial, and I'll probably be doing some more on what it means to be coprime, and talking a bit more about what rational numbers are in general in terms of their properties. Okay, if you enjoyed it, please comment, rate, and favorite, and be sure to subscribe to the channel if you haven't already. Alright, thanks, bye.